common names. With the way the exam will be worded, most of the questions we have the names. And then if it doesn't have the name, we'll have the symbol. You just need to look for the symbol. So I'm going to open the practice exam next on Monday so that you will have an idea of what the exam will look like. So I will still talk about the periodic table when we get to chapter 3. We need our periodic table in chapter 3. We need the atomic masses here. All right, for acid nomenclature, this is how we name acids. Basically, an acid is a compound that has H. So in the context of this chapter, acids are those molecules that have H in them. The first element should be H, because when acid ionizes, they produce hydrogen ions, or we call them hydronium ions. So acid will have H before it. So if you are told to name something like this, the question will be very clear, because this could be hydrogen chloride. But if you are told to name it as an acid, then you call it hydrochloric acid. Yes, the ones with the names, the atomic masses don't match. We need the ones I have on there is the one we use for our exams in chemistry because of the atomic masses. The approximation. I will talk about that when we get to chapter 3. So when we name acid, when an H in the acid is combined with a single anion, we basically call that we name it. We start with hydro. We start with hydro for that one. And if it is combined, if the H is combined with a polyatomic ion, then there's a different way by which we name it. So, for example, we name it based on the name of the polyatomic ion. ClO is a polyatomic ion, basically, and it's called hypochlorite. So when we name the acid, it's hypochlorous acid. ClO2 is chlorite ion. And when we name the acid, we call it chlorous acid. Now, ClO3 is the polyatomic ion is chlorate ion. We name the acid chloric acid, and ClO4 minus is perchlorate ion, so we name it perchloric acid. So we basically need to know how to name the ions. When you remember how to name the ions, you will basically remember how to name the acids. So lastly, in this chapter, the names that you also need to remember is nomenclature of organic compounds. So for the purpose of this class, we're only looking at the introduction to organic chemistry, which is a study of carbon. So the very thing that we learn in this chapter is the study of hydrocarbons. So basically, the simplest hydrocarbons are the alkanes, and the reason why they are called hydrocarbons is mainly because they have C and H in their molecule. So this is a structural way of writing them. So you basically need to just remember the first 10 hydrocarbons from alkane all the way to decane. And also for the alcohol is derived from alkane in the sense that the last letter is replaced with an ol. So basically an alcohol has OH in place of the H of the alkane. This is methanol, ethanol, and this is 1-propanol. So as far as nomenclature, that is what we need to know for the alkanes, and this is what we need to know for the alcohols. Okay, so we're going to round up chapter 2 right now. We're pretty much done with chapter 2. We need to move to chapter 3, mainly because chapter 3 is a little bit, it has a lot of calculations in there, and we need to get a good understanding of what chapter 3 is all about. All right, so we are going to do some practice today in the middle. I will just give us some work to do as practice. And next week as well, we're going to be doing the exam review and also practice. So next week will be chapter 3. And also, if we have enough time, we will review the exam. Just basically talk about what will be on the exam and what you need to prepare for, the study guide for the exam. All right, so chapter 3 is all about chemical reactions, and the discussion I put there, I know some of you have been submitting your response to that. So in chapter 3, we are basically learning about chemical reactions and reaction stoichiometry. So basically, we're going to learn about 3 types of reaction in this chapter. Now, stoichiometry, the definition and everything is here. I hope you guys read these before coming. So basically, in this chapter, we basically examine the quantity of substance, so the amount of the atoms, the molecules that we use in the lab. So we're basically talking about quantitative measurement here. So in this chapter, we're going to be working with a lot of numbers, mainly because we are looking at the quantitative measurement of atoms and molecules. All right, so chemical equation is something that it is very crucial in chemistry. So you have to know how to write simple chemical equations and also how to balance those simple chemical equations. A very simple chemical equation is a reaction between hydrogen gas and oxygen gas to give us water. Okay, so basically the arrow represents that, well, it's going from the reactant to the product. And sometimes we see a symbol like heat on top of it. So that symbol of like triangle on top of it, that triangle represents heat. All right, so before we go to balancing chemical equation, you may see something like this on some chemical equations, like a triangle like this. If you see a triangle, it represent that heat is being applied. Okay, it represents that heat is being applied. So these are the reactants and these are the products. All right, so we're going to look at how to balance chemical equation. Now, we learned about law of conservation of mass or law of conservation of matter back in chapter 1 as well. So we are going to kind of, with our background in that law, is the background in which we have to consider whenever we want to balance chemical equations. So we balance chemical equation because of the law of conservation of mass. Okay, that means that the amount of reactants you start your reactions with should be the amount you produce. So if you started with 5 reactants, you should end up with 5 reactants. Okay, so if you started with 5 and you end up with 4, then you should account for the 1. Okay, so it basically, law of conservation just means that the mass of the matter is conserved, it's not lost. Okay, so it is not lost. So basically, the reason why we balance chemical equations is just for us to obey that law of conservation of mass. So this is a simple way of how to balance chemical equations. Now, there's a PowerPoint I put on Canvas, which basically gives you different ideas on how to balance chemical equation. Just make sure that you look on Canvas. It has a lot of resources that you can use. All right, so this is one of the questions that was asked in the discussion that many of you have been answering, that we do add coefficients instead of subscript to balance. So we're going to do an example of some balancing right now. All right, so after we look at this, we're going to look at some other examples of balancing chemical equations. All right, so this is an example of combustion reaction. Remember, we have 3 types of reaction that is explained, discussed in this chapter. Okay, so one of them is combustion reaction, which is a reaction that involves a lot of heat. So typically hydrocarbons, typically organic compounds, they undergo combustion reaction. So for example, this is an organic compound, this is a hydrocarbon, this is methane gas. When it burns, when it reacts with oxygen gas in the presence of heat, carbon dioxide and water will be produced. Okay, so this is an example of a combustion reaction. So typically, if you are told to balance this reaction, you got to know how to change and work with the coefficients for you to have balanced equation. So basically, when we balance equation, we count the number of atoms on the left, which is a reactant side. That should be equal to the number of atoms on the right, which is the product side. Now, one thing that we also need to include in our chemical equations in chemistry is what we call states. So these are the states of the reactants, the state of the molecule. So this is gaseous state, gaseous, gaseous, gaseous. We also have liquid, solid, and then the other one we have is AQ. Now, AQ just means dissolved in water. We are going to work with AQ entirely in chapter 4. So chapter 4 is all about reactions in aqueous solutions. So we're going to come back to this AQ. Now we're going to do some example on how to balance chemical equations. All right, before we do, I'm just going to go to the whiteboard right now and just going to do some example on how to balance chemical equations. So the first example we are going to do, all right, so we're going to look at this compound. So basically, this C2H6 now with iron. All right, so the product of combustion reaction is typically carbon dioxide and water plus heat because it's an exothermic reaction. Now, keep in mind that when you write the states for your reactions, you got to be in all small caps, small letters. Okay, so this is supposed to be an arrow. So let me try to do an arrow with this. First erase this. So this is an arrow because the arrow tells us that we are going from reactant to product. So if you are given this type of reaction and you are told to balance, this reaction is not, I mean, this equation is not balanced. This is an equation for the reaction between ethane. Ethane, this is the second member of the of alkane series. It's an hydrocarbon. So reacting with oxygen in the process of heat to give us carbon dioxide and water. So to balance this, I gave us a very good PowerPoint again on Canvas in module 3, whereby you learn how to balance. Whenever you want to balance combustion reaction, which is very common, you want to make sure you leave this O2 alone and balance it last. Leave the O2 alone and balance it last. Try to balance other things that is not O2. Okay, so balance other things that is not O2. So I mean, typically we tend to balance other things that is not oxygen and hydrogen first, unless that's all we have in the reaction. So here we have carbon is 2, we have 2 carbons here, and we have 1 carbon here, so the carbon is not balanced. We have 6 hydrogens here, 2 here, the H is not balanced. We have the 2 oxygen here, and we have 3 oxygen here, so the oxygen is not balanced. Okay, so if we want to start balancing from carbon and say, let's say we put our 2 here. All right, we put 2 there, and then if we put 2 there, let's just see what we have. Now the carbon is balanced, the H is still not balanced. Like I said, we'll leave the O2, this middle O2, but then this O2 is still not balanced. So the next thing we can do is if there are 6 H's here, we can go ahead and put 3 H's here. Now remember that balancing of chemical equation is trial and error. You work with a coefficient back and forth till you get it balanced. And when we balance, it has to be the lowest whole number ratio. All right, so we put 6 here. So let's see what we have. 2 carbons on the reactant side, 2 carbon on the product side. 6 H's here, 6 H's here. 2 oxygens here, and here we have 4 plus 3, 7 oxygens here. So the oxygen is not balanced. Like I said, we'll leave this O2 alone. Now because that 7 is an odd number, it's difficult to balance whenever you have odd numbers. A trick to this, now the reason why I chose this example is because this example is a little bit tricky. That's why I chose this example. Other ones will be easier than this. So now we have 7 oxygen on the product side. So basically, I mean, 7 is an odd number. The only way we can make this 7 is to put 7 over 2 here. So let me write this very well. This is 7. And then you're going to see how we're going to get rid of this fraction as we go along. Okay, so we put 7 halves there. Okay, now if we put 7 halves there, the reason why we put 7 halves is because we have 7 oxygens on this side. Because 7 is an odd number, it's hard to get the half of it here. So we put 7 halves here. So when we put 7 halves here, we go ahead and multiply everything by 2. We multiply everything by 2. No, these 2 will not cancel out. These 2 will not cancel out. We go ahead, multiply everything by 2. So when we multiply everything by 2, we put 2 here. When we multiply this by 2, this 2 we cancel with this one. So that this 2 we cancel because we're multiplying everything by 2. Now, if we multiply this by 2, 2 times 2 is 4. So I'll go ahead and change this to 4. If I multiply my 3 by 2, 2 times 3 is 6.
Position function.
Okay, so I want to clean this out to look nice. So let me go ahead and clean this out. So since I've crossed out the 2 here, only the 7 will be left. Remember that the 2 crossed out. I multiply everything by 2 because I had 7 on the product side, and the only way I could do this is just to kind of manipulate my way around and multiply. That multiplying by 2 is just to find a way of getting rid of the fraction because we can't leave fractions there. So that's just going to be 7. So that is just the 7 will remain there. So now I know the 7 looks somehow. All right, let's count everything. 4 hydrogens here. 4 carbons here, 4 carbons here. 6 hydrogens, 12 hydrogens here. 2 times 6 is 12. Here, 6 times 2 is 12 hydrogens. Now let's go to the oxygen. 7 times 2 is 14 oxygen. Let's count here. 4 times 2 is 8 oxygen plus 6 is 14 oxygens. So this is balanced. It is balanced. So that's how we balance chemical equations. Now, like I said, this example it might be a little tricky ones. The other ones that we normally get, yes, we multiply by 2 to get rid of the fraction and get rid of the 2, exactly. Now, like I said, this is just a tricky questions. The other ones are typically easier than this one. And the example given to you guys in here, this example is much easier. We don't have to use fractions, and I will explain. The one now is the one that you have to kind of fractions to because it's kind of difficult when you have odd number. So when you have odd number, we kind of use fractions to kind of manipulate our way around. Of course, if you know other way by which you can do it, as long as it's balanced, you don't have to use fraction. But fraction is an easy way to do it. Now, this one here, we don't need to use fraction. So this one here, if we were to balance this one, this does not require any fraction. So I'm going to give us another one to balance that would not require fractions. So let me just open the whiteboard again. So this one I'm going to give us is one of the reactions that we are going to do in when we get to chapter 4. So this is a reaction between sulfuric acid, H2SO4, and sodium, we probably use the one sodium hydroxide, reaction of a strong base and a strong acid to give us salt and water. When it comes to states, this is going to be like a progressive learning for you to know which state is what. So we keep learning how to which one is which state. Because you may be wondering, why did I put AQ here? Don't worry about that. We'll talk about that in chapter 4. We talk about why is AQ here. So don't worry about that. The main thing you worry about in this chapter is how to mainly balance your chemical equations. Oh, okay, sorry. All right, so this little thing here represents arrow. Let me try to just put my arrow there so it will not be confused. So this reaction here is a reaction between a strong acid and a strong base. We must learn how to see balance and how we can. All right, let's just see if this is balanced. We have 2 hydrogen plus 1, making 3 hydrogens on the left. On the left side, and here we have 2 hydrogens. We have 1 sulfur, 1 sulfur, 1 Na, 2 Nas, and we have 5 oxygens here, and then we have 5 oxygens here as well. So it seems as if like I said, we leave oxygen and H alone. So leave hydrogen and oxygen alone and try to balance them last. Balance other ones first. Typically, because oxygen and hydrogen, they typically occur a lot in the reactions. They are very popular in reactions. Okay, so here we have two A, but it seems as if there's just one Na here. So we can start off by just kind of putting 2 here. All right, if we put 2 there, it looks like the Na is balanced. So now let's see what else needs to be balanced there. So the Na is balanced. Let's just look at the hydrogen. We have 4 hydrogens here, and we have 2 here. We have, let me see, 4 plus 2, 6 oxygens here. So if we go ahead and put 2 here, so now we have 2 hydrogen plus 2 here, making 4 hydrogen. So there's 4 hydrogen here because 2 times 2 is 4. 1 sulfur, 1 sulfur. 4 plus 2, that is 6 oxygens. This is also 4 plus 2, 6 oxygens. And then yes, we are balanced. So remember, the coefficient goes for everything. So yes, this is balanced. Okay, so you can see this one we didn't need to do any fraction. These fraction ones are not that common, but then we still use them. These are the common ones that we typically see. So, but I gave you this example because it will be tricky. Most of the ones may not require us to do fractions. We just put our whole numbers there, and then we should be balanced. Okay, so we're going to move on quickly. And then, so basically, I expect you guys to read all 3 types of chemical reactions and be able to get yourself used to. We have all the notes for us on Canvas. Okay, so combustion reaction, that is an example of it. For example, reaction between magnesium and oxygen gas will give us magnesium oxide. Any reaction that involves 2 reactants and 1 product. So whenever we form 1 product, we say that is a combustion reaction. So decomposition reaction typically involves 1 reactant breaking down into products. So an example of this is used in airbag, whereby sodium azide releases nitrogen gas quickly. So sodium azide NaN3 is used in airbag. So whenever someone gets it in a crash, and then the airbag just releases the nitrogen gas. So the nitrogen gas is what fuels the airbag, not oxygen gas, because oxygen gas is very reactive. So they rather use nitrogen gas to fuel the airbag whenever a crash happens. So just keep in mind that decomposition reaction involves 1 reactant breaking down into 2 products. And so this is an example of decomposition reaction. And like I said, whenever you see triangle like this, it means heat is applied to the reaction. Heat is applied to the reaction. Another example of decomposition reaction is the heating of metal carbonate, like calcium carbonate. When you heat it, you form calcium oxide and carbon dioxide. And lastly, combustion reaction. Basically, these are very high energy reactions because they involves a lot of release of energy in form of heat sometimes. And combustion reaction often involve using O2 in the air as a reactant. So whenever you use O2 in the air as a reactant, you form carbon dioxide and water. So combustion reaction, the product is always carbon dioxide and water. So let's just kind of summarize all 3 reactions. Combination reactions involve reactants coming together to form 1 product. Decomposition reaction involves 1 reactant breaking down into 2 different products. And combustion reaction involve oxygen gas is being used as one of the reactants, and typically the hydrocarbons are the ones that undergo combustion reactions. So this is propane, like propane that we use heating. So basically, propane gas reacting with oxygen to give us carbon dioxide and water. This reaction will not just occur, you have to apply heat, okay? And this reaction, we call it an exothermic reaction because heat will be evolved. Heat will be evolved as part of the product. Heat will be evolved as part of the product. So that's an example of combustion reaction. So just make sure that you read all these types of reaction, it's all about, and on the PowerPoint and also in the book. All right, so we want to go to formula weight now, and then I'm just going to kind of show the periodic table right now. So basically, this periodic table, like I said, the way the question will be worded in the exam, it will kind of say the names of the element and or the symbol. Most of the question will say that. But also keep in mind that common elements, like all those common ions, the element that it contains that we discussed on Monday, as a first year chemistry student, you got to know the names of some common ions. For example, we should know like things like hydrogen, lithium, carbon, nitrogen, oxygen. You should know without having to, if somebody asks you what does O stands for, you should know it's oxygen. Okay. But again, most of the question, the way they will be worded, they basically say the names. And if it doesn't say the name, you can easily look for the symbol here. Where the main thing that we use the periodic table for in this course is to be able to get the atomic masses. The atomic masses in this periodic table is consistent with the questions in the exam. So that's why this is the one that we typically use in our exams in general chemistry 1. So again, this is the one that we typically use. If you don't know the name of it, basically, like I said, in the exam, most of the questions will have the names on it. So this is the periodic table, and then these are the atomic masses. This number here are the atomic masses that we basically use. So from chapter 3 all the way down, we are going to be needing these atomic masses because we do a lot of calculation in this course. And these calculations, we basically need our periodic table to do our calculations. And what we need our periodic table for is just for us to get the atomic masses and also to be able to get the charges as well, like we did last week. So let's look at one of the first things we are going to do. Remember, we said that this chapter is all about quantitative description of the atoms and molecules, right? So we've learned about the qualitative description. Now we are counting them because we are counting them because in the lab, if you go to the lab and you want to make water from H2 and O2, you got to measure the mass of H2, measure the mass of O2 for you to be able to react them together. So in the lab, in real life, we measure. That is why from this chapter downwards, we basically use our atomic masses because in real life we measure, and we got to know that if we have this reactant, how much product are we going to have? That is why this chapter is very important. The word stoichiometry is just a big word. It's just counting atoms and determining the amount of products we get from our reactions. All right, the very first thing we want to look at is formula weight, which is a sum of the atomic weight for the atoms in a chemical formula. For example, we know that, from chapter 1 and chapter 2 as well, we learned that the unit of an atom, of one atom is AMU, atomic mass unit. So we're going to see that when we actually go to the lab and work in real life, we don't use atomic mass units because atomic mass units refers to just one atom. So it's just, we can't see an atom. It's incredibly small, right? So we use grams in the lab. If you've been to the chemistry lab before, we use our balances to be able to measure, and those are in grams. So we got to know how to convert atomic mass unit to grams. And the bridge between atomic mass units and grams is what we call the Avogadro's number. We're going to get to that in a minute. First, let us see how we determine formula weight using just atomic mass units. So if you are told to find the formula weight of H2SO4, this is sulfuric acid. All you do is this. You look on your periodic table, you find H. The atomic mass for H is 1.0079 something. You just kind of approximate it to one decimal place. Okay, so 2 times 1 plus 32 is the 32.1 is the atomic mass for sulfur on the periodic table, plus 4 times 16.0. So we approximate the one on the periodic table to 16.004 for oxygen. And then when we add all that together, we have 98.1 atomic mass units. Now, the formula weight is typically used for ionic compounds, and the formula weight, we use it sometimes for molecular compounds, but then sometimes we call it using for ionic compounds. Molecular weight basically is a sum of the atomic weight of the atoms in a molecule. It is typically almost the same thing as the formula weight. Okay, it's almost the same thing as the formula weight. So like I said, formula weight, we typically use them more for ionic compounds. So the molecular weight of glucose is 180.0 AMU. AMU stands for atomic mass unit. All right, so we're going to do these. Then after we are done with this, we are going to do some calculation because like I said, this course can do some calculations before we keep going. Now that we have learned how to do formula weight and molecular weight, which is essentially the same thing, we want to learn how to calculate percent composition. So basically, the percent composition is the percentage of an element in a compound. So for example, if I say, what is the percentage of oxygen in water? This is how we find it. We count the number of the atoms, and then we multiply that by, this is supposed to be the atomic mass of the atom divided by the formula weight of the compound times 100. So that is how we find the percent composition. So for example, this is calculating the percent of carbon in glucose. So basically, the formula of glucose is C6H12O6. So 6 times 12 divided by the total mass of glucose is 1, it is 40%. So with that being said, we are going to do some calculation. Before we get to Avogadro's number, let us do some calculation first. And I hope we all have a calculator with us because we're going to do some calculations now. All right, the first thing we are going to look at is calculating the molar mass of calcium nitrate. Now, this example was given initially. So this is how we calculate the molar mass of glucose. So to calculate the molar mass of calcium nitrate, what we do is that we grab our periodic table. The molar mass of calcium on the periodic table is 40.1. Let me use the other one to write. I think you guys see this one's better, so let me just use this one. All right, so we have 40.1. That is the mass for calcium plus. Now, whenever you have a parenthesis like this, we use the regular calculator for the exam, or unless nothing should be programmed in the calculator for the exam. So the molar mass, the atomic mass for nitrogen on the periodic table is 14.0, but remember we have 2 nitrogens there. We sort of multiply that by 2. So let me just write the multiplication out clearly so that we understand it better. And then plus the molar mass of oxygen is 15.999. We typically approximate to 16.0. So oxygen is 16.0. And all in atomic mass units. But we have, see, whenever you have things like this in the parentheses, 3 we multiply by 2 in 6. So we multiply this by 6. And everything should be in atomic mass units, AMU. We leave our final answer in 1 decimal place. Okay, so can anyone do that and tell me what you get for your answer? All right, good. So equals 164. All right, very good. 164.1 AMU. So that's how we find the formula weight. Or I mean, the molar mass. That's just how we find the molar mass. And this example is given here. Okay, so I think I need to go back, and I think I'm skipping some of them. So that is one example. We are going to go back now and do some in the beginning here. There's something I'm looking for. Okay. All right. So before we go there, please make sure that you try this at home. And if you're having problem with the balancing, just let me know. Try these three questions at home based on the way I showed us today on how to balance chemical equations. Okay, so writing balanced equations for combination and decomposition reaction. So basically, writing equations is something that we keep learning as we go in this course all the way down. As a beginner, we just need to learn that whenever, for example, in this question, write the combination reaction between lithium metal and fluorine gas. And basically, lithium metal is Li plus fluorine gas is F2. Remember, fluorine is one of those element that exists as diatoms. So the product is lithium fluoride. Now, this is a combination reaction because we have these two reactants giving us one product. And then this second one, the decomposition of barium carbonate, we're giving us barium oxide and carbon dioxide. Okay, so like I said, when it comes to writing equations, we kind of keep learning. This chapter is the beginning. We're just going to keep learning to the end of this course. Okay, so what the main thing that we need to know here is to be able to identify those types of reaction and writing simple combination reactions. Okay, so this is the one I was actually going to do as at first. All right, so this example is already given to us for this example here. We are going to try to do this practice one here. We're going to do practice one here, this one. So I'm just going to go onto the whiteboard and just show this right now. Now we want to write the correct formula weight for calcium phosphate. The correct formula weight for calcium phosphate. Of course, we know that calcium phosphate, this is the formula of calcium phosphate. So we remember that calcium is right there in group 2. All right. Let me use the smaller one. Okay. So let me write the question we are doing. So the question is calculate the formula weight of calcium phosphate. Now remember, this is not complete. Now remember that phosphate has -3. So that is why it's a polyatomic ion with -3. So that 3 comes here. Calcium has +2. So that 2 will come here. So this is the formula of calcium phosphate. The question is calculate the formula weight of calcium phosphate. So to do that, we go on a periodic table. We look for Ca. Ca is right there, and the molar mass, the atomic mass for Ca is 40.0. So it's 40.078. So just approximate it to, like I said, we can leave it in one decimal place. 40.1 multiply by 3. Or you can, if you understand it better that way, you can write the 3 first because that is the number of atoms. So that 3 represent the number of calciums we have there. So multiply by 40.1 plus this has to have 2. I don't know how this 2 got erased. This should have 2. All right, so phosphorus here, P stands for phosphorus, and that is just going to be 2 times on the periodic table. The atomic mass for phosphorus is 30.97, so we just put as 30.9. Plus oxygen is 4, but because there's a 2 out here, we multiply 2 times 4 is 8. So that'll be 8 times oxygen on the periodic table is 16.0. So, and everything is to be an atomic mass unit since we haven't done the Avogadro's number yet. So everything should be in atomic mass unit. Okay, so can we do that and let me know what you get for that? Okay, good. Okay, any question on this? Any question on that? So if you have any question, you can always type it out to let me know your question. If you have any question, you can always type it out. Okay, kind of missed that. Okay, so that answer for that, no, this was the not the one I wanted to. Okay, so this is the one that we just do. So this is the answer for that is A, approximately 310.2 AMU. Now you can do this on your own at home. And if you have question, you can always bring it or you can email the question. All right, so we want to calculate percentage of an element in a compound. The example given here is calculate the percentage of carbon, H, and oxygen in sucrose. This is sucrose. And this is basically how it's been done. So we're going to do another question right now. I believe we do this one. We do this practice one. So we do this practice one here. Now, the practice one says, what is the percentage of nitrogen by mass in calcium nitrate? The very first thing you want to do is to write down the formula of calcium nitrate. Calcium nitrate. Now, remember that calcium nitrate comes from calcium, which is in group 2, and nitrate is NO3 minus. Nitrate is a polyatomic ion. So this is what the formula of calcium nitrate will look like. Because calcium has +2 charge, nitrate has -1 charge. So basically put 2 here. So the question is, what is the percentage of nitrogen by mass in calcium nitrate? So that example here that was given to us previously is exactly what we are going to follow here. So nitrogen here, there are 2 atoms of nitrogen. The very first thing you want to do from that formula is that remember that percentage by mass is going to be the number of atoms of the element we are looking for times the atomic mass divided by the total formula weight of a compound times 100%. So the very first thing you want to do is, can somebody calculate what is the formula weight of this compound? What is the formula weight of calcium nitrate? All right, good. It's 164.1 around that. Yes, we just leave it as 164.1. Like I said, for the exam, since it's multiple choice, the options will be distinct. So you won't have answers close together. Does that make sense? So you will not have answers close together to be confusing. The options will be very different from each other. All right, so this is 164.1 atomic mass units. To calculate the percentage of nitrogen by mass in calcium nitrate, what we do is this. Well, there are 2 nitrogens here, so we say 2 times 14 because the atomic mass for nitrogen is 14.0 atomic mass units divided by, so this is AMU, divided by the total mass of calcium nitrate. Since we want to find the percentage of one element in the entire compound. We just find atoms of that element. We have 2. We multiply it by its atomic mass that we found on our periodic table. Then we divide by the total mass of that compound, which is calcium nitrate here. Then we multiply by 100%. We multiply by 100%. Okay, very good. So that is the answer we get for that. So it's 17.1. So this is the correct option, 17.1. So this is how we calculate the percentage of an element in a compound. Percentage of an element in a compound. You first calculate the mass of that compound, and then you go ahead. Now, this is also an atomic mass unit. Then you divide that mass by the mass of that element by the total molar weight. If it were to be just calcium we are looking for, we don't have to put 2 because it's just one calcium. We're just going to do 40.0 over 164.1 times 100%. Okay, so right now we're going to go back to the lecture and finish up what we are talking about and just look at how we can relate atomic mass units to grams, because grams is what we use in the class, in the lab, not atomic mass unit. Atomic mass, one atom, one atomic mass unit. Even if it's 1,000 atomic mass unit, we can't see it because atoms are incredibly small. They're incredibly small. So we need special electroscope to be able to see atoms. All right. So the relationship between atomic mass unit and the grams that we talk about that we use in the lab, the bridge between them is the number called the Avogadro's number. So this is just a very good illustration. Now, a single molecule of water, H2O, right? The molecular weight of water is 18.0 atomic mass units. That's just one molecule of water. Nobody can see one molecule of water with their naked eye. It's got to use some kind of electroscope to do that. Now, but in the lab, we work with water, right? We drink water every day. The relationship between this one molecule and the one that we can see is called the Avogadro's number. 1 mole of water contains 6.02. Now, this is supposed to be 6.02. 6.02 times 10 to the 23 atoms or molecules. Now, 1 mole of water in the lab is equivalent to the molar mass of water, which is 18 grams. That 1 mole of water, as you were saying, a laboratory size in a beaker like this, has 6.02 times 10 to 23 molecules of water. So you can see that is incredibly, that tells you how small atoms and molecules. So just one looks like a beaker full of water. It's just 18 grams of water. It contains 6.02 times 10 to the 23 molecules. That is 6.02 times 10 to the 23 small one H2Os, because one molecule of H2O is just 18.0 AMU. So what that means is that the bridge between AMU and gram is the Avogadro's number. That Avogadro's number is the bridge between AMU and grams. And that is what we are going to be working with from now on. We don't work with AMU because all the calculations we're going to do for the rest of this course is talking in real life sense. I see you in the lab. So we use the grams. We use grams to be able to, it will be given. Avogadro's number will be given. You don't have to memorize Avogadro's number. It will be given. All right, so we want to look at molar mass. Now that we have learned the bridge between atomic mass units and grams, and I'm kind of emphasizing on grams because I know many of us are used to grams. So the link between the atomic mass units and grams is the Avogadro's number. And we're going to do a bunch of calculations so that we can know exactly how to convert between AMU and grams. So in this chapter, we do a lot of conversion in this chapter. Now, a molar mass is the mass of 1 mole of a substance. So basically, the molar mass of an element is the atomic weight of the element from the periodic table. So if it's diatomic, it's twice. So the formula weight in AMU would be the same number as the molar mass in grams per mole. So for example, the formula weight of one molecule of water is 18.0 AMU. The molar mass of 1 mole of water will be 18.0 grams per mole. Whenever you see grams per mole, this is the unit for molar mass. So you got to remember that grams per mole is the unit for molar mass. Now here we want to look at the mole relationships. Now the abbreviated form of mole is MOL. We use that a lot. Now let's just look at all of this. So basically for atomic nitrogen, the formula weight is 14.0 AMU. The molar mass is 14.0 grams per mole. And in 1 mole of nitrogen here, we have 6.02 times 10 to the 23 nitrogen atoms. Same thing, let's look at nitrogen molecule here. So nitrogen molecule, the formula weight is 28.0. The molar mass is 8.0. In 1 molar mass, in 1 mole of N2 N2 molecule, we have 6.02 times 10 to 23 N2 molecules and 2 times 6.02 times 10 to 23 N atoms. So basically on and on like this. So that Avogadro's number helps to serve as a bridge between the atoms and the moles. For example, this is barium chloride. So 1 mole of barium chloride contains 6.02 times 10 to 23 formula units. Now, formula units, we use that again for ionic compounds. So because barium chloride consists of barium ions and chloride ions, so each of those ions also have 6.02 times 1 mole of barium chloride consists of 6.02 times 10 to 23 barium ions, and also 1 mole of barium chloride consists of 2 times 6.02 times 10 to 23 chloride ions. So we're going to do some calculations right now. The very first one we are doing here is how many atoms in 3 grams of copper. If you are told to calculate how many atoms in 3 grams of copper or anything that is being asked, this is the calculation steps. Now, we are going to spend a lot of time on this type of calculations today. Of course, we don't have a lot of time left today. Monday, we're going to spend a lot of time on calculation back and forth. Converting back and forth in this chapter. So the very first thing you do is that we basically go through, we use this chart here. Okay, you don't have to memorize this chart at all. We are going to use this in this class, and when we come next week, I'm going to give us a short practice to do during the class here. So here we have 3 grams of copper. We first convert the 3 grams to mole. So we multiply it by 3.5 grams of copper because on the periodic table, the atomic mass of copper is 63.5 grams. It's equivalent to 1 mole of copper. And then it says 1 mole of copper has 6.02 times 10 to 23 atoms of copper. So that is the answer for that. All right, before we even go to empirical formulas, we are going to do calculations. So like I said, it's just all about the calculations in this course. So right now I'm uploading the work example so we can see what to do here. So let's go. I think we did that. Okay, so the very first one we are going to do here. All right, so we're going to do this right now, this question here. All right, so let us do this one. How many sulfur atoms? And so I'm going to open the whiteboard and we're going to do this one right now. Okay, so the question is, okay, how many sulfur atoms are in 0.45 mole of barium sulfate? All right, so to do that, this is what we need to remember. We are given the question in mole. So the very first thing you want to write is that you want to write that 0.45 mole we're given the in mole, and then we are told to find how many sulfur atoms are there. Whenever you see the word atoms, then you got to remember we're going to use our Avogadro's number. So 0.45 mole of barium sulfate okay, so we multiply that by, we say that 1 mole of barium sulfate, 1 mole of barium sulfate contains how many moles of sulfur atoms? It's just 1 mole of sulfur atoms because we have just 1 sulfur there. So 1 mole of barium sulfate contains only 1 mole of sulfur. 1 mole of barium sulfate also contains 1 mole of barium. 1 mole of barium sulfate contains 4 moles of oxygen. So to know how many moles that it contains, we basically just count how many atoms. So 1 mole of barium sulfate contains 1 mole of sulfur. Now they're asking us how many sulfur atoms. So we are not done with this setup, okay? We are basically trying to convert mole of barium sulfate to atoms of sulfur. So we say that 1 mole of sulfur, this is when we use our Avogadro's number. 1 mole of sulfur contains 6.02 times 10 to the 23 atoms of sulfur. And I will explain how we go from given unit. All right, so the given unit is mole of barium sulfate, and what we are told to find is atoms of sulfur. So all the units should cancel out. The only one that should remain should be the atoms of sulfur. So this is the atoms of sulfur. That's just, yes, that is correct. So that is 2.7. So our final answer will be 2.7 times 10 to the 23 atoms of sulfur. Any questions on that? So the given unit should cancel out, and we should only be left with the desired unit. So the desired unit is atoms of sulfur. The given unit is mole of barium sulfate. So that is just basically how we go from mole to atoms. So another question we are going to do right now, we are going to see how we can go from grams to atoms. So let me just go real quick here and show us that question. How we can go from grams to atoms. The one we just did now is from mole to atoms. We can also go from grams to atoms. Okay, before we get here, not this, we've done all of this. Okay, so we're gonna do this. All right, so for this one, if we do the practice one, this practice one, I do it often because the answer is not in the back of the book. So we are gonna do this right now. What is the mass in gram of 6.33 mole of sodium hydrogen carbonate? So we're gonna do this right now. So I'm just gonna go to the whiteboard and show this right now. So the question is, what is the mass in gram? It is 6.33 mole of NaHCO3. Okay, so what is the mass in grams of 6.33 mole of sodium hydrogen carbonates? So we are basically going from mole to grams, okay? The one we just did, we went from mole to atoms. That is when we needed our Avogadro's number, okay? So right now we are going from, what is the mass in grams of that? So we're going from mole to grams. So we're going from mole to grams. So to go from mole to grams, all we do is to multiply by the molar mass conversion factor. The molar mass conversion factor that we basically use is that 1 mole of any element, 1 mole of a compound, it causes the molar mass. So basically, I'm just going to use the other one to write this. So we're going to start off with 6.33 mole. So 6.33 mole of sodium hydrogen carbonate. We want to convert that to the mass of sodium hydrogen carbonate. So this is something that is very common that we do a lot. We go from moles to mass, and we should also be able to go from grams to moles. All we do is to multiply by the molar mass conversion factor, which says that 1 mole of anything. So this is the molar mass conversion factor, says that 1 mole of a molecule equals its molar mass. 1 mole of a molecule or a compound equals its molar mass. And its molar mass can be found by just using those numbers, the atomic masses on the periodic table. So 1 mole of a compound equals its molar mass. So whenever you are told to convert mole to mass, you basically multiply that mole by the molar mass conversion factor, which says that 1 mole of sodium hydrogen carbonate will be in the denominator here, and then the molar mass will be on top in grams. So what is the molar mass of sodium hydrogen carbonate? Just look on your periodic table and calculate what will be the molar mass of sodium hydrogen carbonate. So you can see that the periodic table, the way we're using it now is we'll use it on the exam. We just find those symbols, and if names is given, the names will be given, or we just find the symbol. So you wouldn't be asked to write the name of an element, in an exam. Okay, so it's somewhere around 83.9 thereabouts. So good. Okay, it looks like majority of us got 84. Okay, let's just do that in one significant. So the one decimal place here. Okay. So what is the final answer for this? Multiply 6.33. Very good. So approximately we will have 532 grams. So approximately we will have 532 grams. So approximately we will have 532 grams. So that's how we go from mole to grams. The other one I want us to see is, I believe that should be the next one, is how to go from grams, to atoms, I believe. I think we did this already. So we did that already. Okay, so we're gonna do this. Okay, we're gonna do this. How many chlorine atoms? We're gonna do this practice 1. How many chlorine atoms are in 12.2 gram of carbon tetrachloride? So I'll just go back to the whiteboard. And I'll write the question down here. Okay, that is a question. How many chlorine atoms are in 12.2 gram of carbon tetrachloride? So here we're trying to go from grams all the way to atoms. We're going from grams all the way to atoms. So what we do is that we just start our step one by one. We go through it just one by one. So we have 12.2 gram. This is our given unit, 12.2 gram of carbon tetrachloride. We want to turn that gram to mole first because the relationship between grams and atoms has got to be the mole. And then when we turn it to mole, we will now relate that mole to the atoms using Avogadro's number. So whenever you see atoms, then it has to do with Avogadro's number. Okay? So 12.2 gram of carbon tetrachloride multiplied by, what is the molar mass of carbon tetrachloride? What is the molar mass of CCl4? Anybody find that? Molar mass of CCl4. Very good, 153.8. Okay, so that's 153.8 gram. That contains 1 mole of carbon tetrachloride. Now that we have turned our mass to moles, remember I said whenever we are looking to the number of atoms, we first need to convert our grams to moles, okay? So right now we have converted grams to mole. Now we keep going. Now these steps, you could break it down or you could do it in one line, in just one straight step. All right, next thing we're going to do, we're going to say that, well, 1 mole of carbon tetrachloride, 1 mole of carbon tetrachloride contains 4 moles of chlorine because there are 4 chlorine there. So it contains 4 moles of chlorine. And then 4 moles of chlorine. And then lastly, we say that 1 mole of chlorine So again, we're still going to do a lot of examples next week in case you didn't get this one very well. 1 mole of chlorine contains 6.02 times 10 to the 23 atoms of chlorine. Okay, before we do our final answer, we want to make sure that all our units crosses out and all we have left is our desired unit, which is the atoms of chlorine. So what would be the final answer for that? All right, very good. So that's just going to be 1.91 times 10 to the 23 atoms. Of chlorine. Atoms of chlorine. So this is how we go from grams to atoms. We first get it grams to mole, Then we know that once we get to grams per mole, we know that we are looking for the atoms of chlorine inside CCl4. So we say 1 mole of CCl4 contains 4 moles of chlorine. So once we get that, we now say 1 mole of chlorine contains 6.02 times 10 to the 23 atoms of chlorine. Atoms of chlorine. So do we have any questions? Like I said, next week I'm going to give us some work to do during class next week. All right, so we want to, before we close, we want to just quickly look at empirical formula and how we go about that empirical formula. Okay, so basically you remember that we talked about empirical and molecular formulas in chapter 2. So that's just like the theoretical part of it. So empirical formula is actually determined in the lab. The word empirical it means experimental. It's determined in the lab. We can only determine empirical formula of something experimentally. All right, so we're going to look at how we calculate empirical formulas. This example given here is the example we are going to use. The compound para-aminobenzoic acid, listed as PABA on the sunscreen bottle, contains of that amount of carbon, hydrogen, nitrogen, and oxygen. Find the empirical formula of PABA. Now, whenever you see percentages in chemistry in a molecule like this, all of them should add up to 100. So we assume 100 gram of the compound is present. So we assume 100 gram of the compound because whenever you see percentages, everything should add up to 100. So we're going to turn this percent to gram. To find empirical formula, we got to divide each of these parts, each of these numbers, which, like I said, is equivalent to the grams because everything equals to 100 gram. We divide each of these by the molar masses of this element, and then we keep going. So this example is shown here. So we assume 100 gram of that PABA. Now we divide it by the gram. Well, here the molar mass conversion factor, you multiply it by you multiply the molar mass conversion factor by the gram. Now I'm going to give us a formula right now, and this formula is very useful. So I'm just going to kind of go to the whiteboard to give us the formula on how to get number of moles. Number of moles is mass. Well, when I'm done with this, I'll give us. Moles is the same thing as mass over molar mass. To find moles is mass over molar mass. Once you start getting used to this, you will just know easily that moles is mass over molar mass. So if we divide each of those grams, which was, like I said, was percentage, but we assume is 100 gram because everything add up to 100. So whenever you see percent chemistry like that, is a percent mass, everything add up to 100, you just turn that percent to gram. So we divide each of these by the molar masses and we get these numbers, the moles. Now we divide by the smallest number of mole. The smallest number of mole is the one for nitrogen. So when we divide by the smallest number of mole, this is what we have. So we now use what we have as a subscript in our to get our empirical formula. So basically we can easily approximate. We typically approximate if it's between 0.1 and 0.9. If it's not between 0.1 and 0.9, we multiply by a whole number, a small integer. We're going to do that next week to be able to get it down to a number that we can approximate. All right, so those number that you get when we divide by the smallest number of moles, those number will serve as the subscript. So this is the empirical formula for that sunscreen that we're talking about. So we are going to stop here today. On Monday, we are going to continue and do a lot of calculations. I'm going to give us some things to do during the class, and I'll give us some time to do it, like a practice quiz, but it's not graded, it's just for practice. So so that we can, rehearse everything that we have talked about here. So I said I was going to give us the formula for finding moles. So another formula that we use for finding moles is mass in gram divided by molar mass in grams per mole. So you can write this formula down. Moles equals mass over molar mass. So this formula is very useful in this course. So any questions so far on what we have done today? Okay, so I will see you guys on Monday. So just again, I mean, review everything we do. If we have questions, bring next week will be more of review for the exam. So bring it next week, and we're going to do a short practice quiz during the class next week. So if we don't have questions, so I will see you guys. Remember to submit your work that is due. All right, I will see you guys next week. Have a great weekend. Bye.